Good morning, everyone. This is Professor Sagar Patil from Department of Mechanical Engineering, Progressive Education Societies, Modern College of Engineering, Pune. I welcome you for this online session on design of transmission systems, and our today's topic is design of gears. So let us start with the first slide. Before starting with the actual topic, I want to discuss or I want to throw some light on the syllabus details of this particular semester. So as usual, we have the subjects for the semester, and among the subjects, design of transmission systems is the one which carries total weightage of 125 marks and total credits are 4. Total theory lectures per week will be 3 and total practical hours per week will be 2. So every student must understand or must know the course outcomes of this particular subject, that is design of transmission systems. So number one is to apply the principle of spur and helical gear design for industrial applications. Course outcome number 2, to explain and to design the bevel and worm gear considering the design parameters as per the design standards. CO number 3, to select and to design rolling and sliding contact bearings from the manufacturer's catalog for a typical application considering suitable design parameters. CO number 4, to define and to design various types of clutches, brakes used in automobiles. CO number 5, to apply the various concepts to design machine tool gearbox for the design different applications. CO number 6, to elaborate various modes of operation, degree of hybridization and allied terms associated with the hybrid electric vehicles. So this is all about the course outcomes. Then coming to the topic, that is spur gears. So before understanding the spur gears, one must know the definition of transmission. So the transmission means to transmit the power or torque from the one element to the another element, and for this purpose we need these kind of elements like gears, pulleys, sprockets. So through these elements we can transfer the power or torque from input shaft to the output shaft. So as far as this topic is concerned, there are the different points which we'll be discussing in detail later on. So starting from the introduction to gears. So in introduction to gears, we will be discussing about these theory contents like gear selection, for which kind of application which gear is suitable, that we must be able to coordinate. Then material selection should be based on the different parameters, that is availability, cost, its functionality, whether it is suitable or compatible with the available manufacturing processes or not. So these are the different parameters which will be important from the selection of the material. Then basic modes of tooth failure. Unless we know the failure, we cannot design that particular element. So we must know this design procedure as well as the basic modes of gear tooth failure in detail, and gear lubrication methods. Of course, the gear is the element which is in contact with the another mating gear, and continuously there is a material to material contact, and power is getting transmitted through this particular contact only, and because of this contact the tremendous amount of heat is continuously generated in that particular system. So there must be some system which can dissipate or extract the heat, and one of them is lubrication. So after these theory points, we will be discussing the analytical terms, that is number of teeth and the face width, then force analysis, beam strength, which is the Levi's equation, velocity factor, service factor, load concentration factor, effective load on the gear, then wear strength, Buckingham's equation, estimation of the module based on the beer and wear strength, then estimation of the dynamic tooth load by velocity factor and Buckingham's equation, then AGMA, that is American Gear Manufacturing association approach for the gear design. For this particular, only mathematical relations are expected. No numerical will be asked in the examination as far as the MOM of BOC is considered. Okay. So this Buckingham's equation and the Leibniz equation are the base on which the design of rest of the gears is also based on. So this will be the common Leibniz equation and Buckingham's equation for rest of the gears, like helical gear, bevel gear and worm gear, which is there in our syllabus. Okay. So as far as the helical gears are concerned, again the same points are there which we discussed in the spur gear. So this is the basic definition of the gear. Okay, so gears are defined as toothed wheels or multi-lobed cams which can transmit the power or motion, or you can say the torque, from one shaft to the another shaft by means of successive engagement of the teeth. Next point is classification. So classification is based on the few factors. First is position of shaft axis. So second one is peripheral velocity of the gears. Third one is meshing of gears, whether it is internal meshing or external meshing. So first point is according to the position of shaft axis. So first position is parallel, second is intersecting, and third one is non-parallel, non-intersecting. So for parallel shafts we can use the spur gears, helical gears or rack and pinion gears. So in figure you can visualize or observe how the stretch spur gears are, how helical spur gears are, how herringbone gears are. Then for intersecting shaft, simply we'll be using the bevel gears and the spiral bevel gears, and for non-intersecting and non-parallel shafts we'll be using the spiral gears or worm and worm wheel or the hypoid bevel gears. Okay. The second parameter is the peripheral velocity, low velocity, medium velocity and high velocity. So there are the different ranges from 0 to 3 meter per second. We'll be using the low velocity gears. For from 3 meter per second to 15 meters per second we'll be using the medium velocity gears, and for the gears which will be rotating at more than 15 meter per second speed, we'll be using the high velocity gears. And as we discussed, the external meshing and internal meshing, that is nothing but the third point on which the gears are classified. After classification, one must understand the basic terms of the spur gear, which is the basic form of the gear. So among these, here you can see the addendum is there, dedendum is there, pitch circle is there. So pitch surface element is there, then addendum circle is there, dedendum circle is there, face width is there, face is there, flank is there. So and from the arrows you can gauge the meaning of the addendum. So addendum is the distance between the pitch circle and the addendum circle. That linear distance is nothing but the radial distance is nothing but the addendum. Same is applicable for the dedendum. Face width is nothing but the total distance between the two faces of the gear, that is front face and the back face. Likewise, different these terms are there. The number one is pitch circle. It is an imaginary circle which by pure rolling action would give the same motion as the actual gear. Then pitch circle diameter. It is the diameter of the pitch circle. Third one is the pitch point. It is a common point of contact between the two pitch circles. Then pitch surface. It is the surface of the rolling discs which the meshing gears have replaced at the pitch circle. The number 5 is module, which is very important. It is nothing but the ratio of PCD, that is pitch circle diameter, by number of teeth, that is Z. So usually we used to call M equal to D by Z. Okay. So and these are the standard values of the modular 1, 1.25, 1.5, 2, 2.5, 3, 4 and so on. Then number 6 is pitch circle. Circular pitch, that is PC. It is nothing but the distance measured along the circumference of a pitch circle from a point on the tooth to the corresponding point on the next tooth. Generally it is denoted by the pi d by z, and the unit of which is pi n. Number 7 is diametral pitch. It is the ratio of number of teeth on a gear to the PCD in mm. It is nothing but the dz by d, or reciprocal of module. So next slide comprises of the, just a minute. The next topic is selection of type of gear. The first step in the design of gear drive is the selection of proper type of gear for a given application. So for this purpose we need the general layout of the shaft. So based on this, again as we discussed, it depends on the orientation of a shaft, whether it is parallel or perpendicular. Then second is the speed ratio, medium, low and high. Okay, this is given in detail. Next is the cost. So it should be cheapest, followed by the helical gears and bevel gears. So spur gears are much less costlier compared to the other types of gears. Then next one is the power transmission. Spur and helical gears normally can transmit the very large power up to the 18,000 kilowatt. However, because of the low efficiency, one gear drive is not preferred for a high power transmission. Then so these are the efficiency ranges given for the different types of gears. Then there are the three standard methods: 14.5 full depth involute system, 20 degrees full depth involute system, and 20 degrees sub involute system. So based on these systems, will be like designing the gears. So for this purpose, first type of the system, that is 14.5 full depth involute system, the basic rack for the system is composed of the straight sides except the fillet arcs. In this system, interference occurs when the number of teeth on the pinion is less than 32. This is satisfactory when the number of teeth on a gears is large. So second is 20 degrees full depth involute system. In this particular system, interference occurs when the number of teeth on pinion is less than 17. Okay. Number 3 is 20 degrees sub involute system. The gears are in this system have shorter addendum and shorter dedendum. And normally we use the first two systems, that is 14.5 and 20 degrees involute, full depth involute. In very special cases or exceptional cases, we deal with this 20 degrees sub involute system. Okay. So these are the ranges of addendum, dedendum, clearance, working depth, hole depth, and tooth thickness are given for these three types of systems. These are the empirical relations. Okay. And I think all of you must know the meaning of empirical relations. Module one must understand in detail. Okay. Selection of the material for the gear, as we discussed, it must comprise of high endurance strength in bending, then high surface endurance strength to avoid the destructive pitting, then low coefficient of friction to avoid the scoring, then consistent thermal extraction. And the different materials suggested for the manufacturing of gears are cast iron, which is easily available. It is available from the grades of FG200, FG260, FG350. So FG200 means the strength of that of this particular material is 200 Newton per mm square. So these are least expensive. Then they have good damping property. Then they can easily cast into the complicated shapes. They have excellent machinability. Disadvantages: these are brittle, bending endurance strength is low. Okay. Second one is steel. Steel is nothing but like alloy of ferrous and carbon. So these are the large number of steels used for the gears ranging from plain carbon steels to highly alloyed steels and low carbon steels to high carbon steels. 50C4, 50C8. So 50C4 means 0.5 percentage of carbon and 0.04 percentage of manganese. Same is applicable for 55C8. Okay. Selection of materials. So after this, we can go to the next material, that is nothing but the non-ferrous metals. Again, non-ferrous metals like copper, zinc, tin, manganese can also be used for various combinations of the gear materials. The common alloy is bronze. Then sintered metals, the sintered gears made by the powder metallurgical processes from the iron and copper powder are used as low cost gears. The strength is not prime consideration. These gears are wear resistant and easy to lubricate. Non-metals like polymers, then bakelite, nylon, plastics. Okay. So after discussing about the materials for the gears, we will be starting with the modes of gear tooth failure. So there are the two types of tooth failure. One is breakage of the tooth due to the static or dynamic load, or it can be called as a bending failure, and second one is a wear failure. So bending failure and wear failure, these are the two broad categories of this particular gear tooth failure. This second type of failure, which is wear failure, can be again subclassified into the pitting, corrosion, abrasive and scoring. Okay, so this is in detail explanation of this types of the gear failure. Last one is scoring. So I think we can stop here, and based on this discussion you can prepare yourself for this particular theory topics which we covered today. And after covering or understanding these topics in detail, we can start with the next topic, that is nothing but the force analysis of the spur gear. Okay, so in the next lecture we will be discussing about this particular analytical part, which is the force analysis of the spur gear. So thank you for your patient listening. See you soon for the next session.